Hey guys, I wanted to explain to you how to add and subtract vectors, okay? So first, before we talk vectors, we actually should talk before of scalar quantities. So what is a scalar quantity? It is a quantity in physics that can be described only by a magnitude. Let's say an example of this can be a temperature, or a volume, or even a mass. These are just some simple examples of scalar quantities. Then, what is a vector? A vector is a quantity in physics that actually has a magnitude, and added to that magnitude, it has also a direction. A simple example of this can be just the velocity of an object. We can say it is going 20 miles an hour to the east. We're given a magnitude, 20 miles an hour, and a direction to the east. All right, let's talk about how we add vectors. Let's say we have a vector A, right? We describe it as an A, and we put a little arrow on top, okay? So A plus B. So actually I got a little ahead there, but when we say A plus B, what we're actually doing is putting one vector's tail in front of the other vector's head, okay? We're putting them in a series. How do we represent the vector A plus B? An addition of vectors is actually a vector itself. How do we represent it? We say, from the tail of the first vector, we draw a line from it to the head of the second vector. And we say A plus B. So this is the sum of vectors in a more conceptual form. So let's try to explain it in a more numerical way. Firstly, we should describe a coordinate system for our problem. So let's say we will use the most common coordinate system, x, and in the vertical we put y. Okay, so let's write our vector. Our vector will be A. How do we add? With a vector B. First, we cannot just simply say from here to here in numbers that easily, right? So what we have to do is actually calculate the components of the vector, how to decompose a vector in its components. Okay, so let's first draw our coordinate system. Let's say x, y, and now let's draw our vector. Okay, so a vector with a magnitude A and a direction of an angle theta from the x-axis to the vector. Okay, so we describe it like this, okay, an angle theta. What are the components of a vector? The components of a vector are like the shadow a vector casts in one of the coordinate system components. So let's say the coordinate x of the vector is actually the shadow of the vector A that it projected on the axis, on the x-axis. Okay, so we call this the x component of the vector A, and we do the same with the y component, okay? And we say, well, this is all this length, okay? And we do the same with the y component of the vector, and we say that the component y of the vector, A sub y, is from the 0 to the shadow that the vector casts in the y-axis. If we move this length to here, we can draw this way. And if you remember from trigonometry class, you probably don't, but I'm gonna make a quick remember. We have here a right triangle, okay? We have an angle of 90 degrees, and we know the hypotenuse. I'm gonna erase this to declutter a little bit. But if you remember from trigonometry, we have that sine of the angle, it's equal to the opposite side, and this is the component y, divided by the hypotenuse. This time, we know that this vector has a magnitude of A. The component, the hypotenuse, sorry, it has a magnitude A. From here, we can solve for the component y, and we will get that AY times sine of theta equals the, A, the magnitude of the vector, we're going to multiply this way, times sine of theta, it's equals to the y component of the vector, We can do the same for the x component of the vector. So the x component of the vector, we write cosine of theta, it's equal to a, the component x, that is this side, divided by the hypotenuse, okay? And it is a again. So we solve again for the component x of the vector, and we see that a times cosine of theta equals the horizontal component of the vector. This is very important, and we have to probably take note of this, okay? Also, let's make a quick check, and you can see here, if we describe the vector from an angle from the y-axis in negative direction, okay, that's something I should mention. So we call the negative direction of the angle, when we describe it, it will be clockwise, okay? And we describe the positive direction of an angle when it's written in counterclockwise, okay? So counterclockwise, positive direction of the angle, and clockwise, negative direction of the angle, okay? And let's say we describe an angle from the y coordinate to our vector, and we say it's an angle alpha. So this angle alpha will actually give us a somewhat different result. We will say that a cosine of alpha equals the y component of the vector, and a times sine of alpha is the x component of the vector. So why is this? This is actually a very common mistake. Don't just remember that the sine goes with a vertical component, with a y component, sorry, and the cosine with the horizontal component. It's also important to know that if the angle is defined from the vertical, we have to look at the trigonometry again. To get this result, we would have to write this. We would say that the sine of alpha is actually equal to the opposite side. And look that now this time the opposite side of the vector is actually a sub x, okay? It's actually the horizontal component. So we have this, the horizontal component divided by the hypotenuse, okay? And the same with the cosine. Cosine of alpha equals this time the adjacent component divided by the hypotenuse. This time the adjacent is not x, but the y component divided by a. And if we solve for this again, we multiply by a both sides, and we actually have a sub y and a sub x. So, going back at again, if I draw the coordinate system, x, y, let's say we have a vector of magnitude 100 meters. Okay? And with an angle of 45 degrees. We want to decompose this vector in its components, and we will say this side will be equal to 100 times sine of 45. Okay? And this component will be 100 times cosine of 45. We put this in the calculator, and we'll say 100 times sine 45 degrees, and we'll say it is approximately 70.7 meters, and this component will be approximately 70.7 meters. Now, let's say we have another vector, okay? I'm gonna write this over here, 100 meters. And now let's say we have a vector that goes along the x-axis. So the angle between the x-axis and the vector of, let's say, another 100 meters is actually 0, okay? So if we actually draw a miniature coordinate system here at the tail of the second vector, we'll have that the vertical will go up, and actually the horizontal axis, the x-axis, will be just above the vector. The vertical component of this vector will actually be 0, and the horizontal component of the vector would be just the magnitude itself. So here we have that the vertical component, A, will be just 100 meters. Okay? So how do we add them? Well, we add the components just like if they were scalars, okay? And we'll say this is 70.7 meters. Oh, that looks 70.7 meters. And this will have a quantity of 100 meters. Okay? And how can I erase this? It's not necessary. And we add as well the vertical components. So we know that this vertical component from the tail of the first vector to the head of the last vector is actually just equal to 70.7 meters, okay? So we just add these two, and we will say that the distance, okay. So in the horizontal axis, we actually just add up these two. So we say that we actually moved 170.7 meters from here to the last position, okay? We can draw this vector from the tail of the first vector to the head of the last vector. Let's say we call this vector A and this vector B. This will be our vector A plus B, and we can call it the vector C, okay? Oh, that looks kind of bad. A short way to write this, and it's actually the most common way, will be to say that C equals, and we write it like this, the horizontal component of the vector and the vertical component of the vector, okay? Cx comma cy, okay? So in this case, we will say that C equals 170 meters, 170.7 meters, comma 70.7 meters. We can actually get the new component, the new angle actually, of this new vector C, okay? This angle, we can call it beta. To get the angle beta, we have to do the same trick we did before, but in reverse. Well, it's not the same, but it's very similar. If we write it again, we know this component that is actually just 70.7, and we know this component that is 170.7, okay? From the tail to the head, from the tail to the head. If you remember, this is a right triangle again, but this time we do not know the magnitude, we just know the components. In this situation, we know the cathetus and the opposing cathetus. If you recall, we can say that tangent of beta equals the opposing component, C sub y, divided in the adjacent cathetus, okay? And it's C sub x. If you recall as well, we can define an inverse function. We can apply the inverse function to the both sides of the equation, and we'll get the beta equals the tangent to the -1, or whichever notation you used, C sub y and C sub x. We can just substitute the values and put it in the calculator. And it equals 22 point, let's round it up to 5 degrees. To obtain the magnitude of the vector, we can say this. We can say that C sub x square times plus C sub y square, it's equal to the hypotenuse. This time is just C square, okay? We can solve for C just by applying the root to the both sides, and we will get that C equals the root of the both components squared, and we just substitute these two values in this equation. And it has a magnitude of just, let's write it here, 184.8. So thank you very much for watching. Please hit the like button, subscribe, and maybe consider giving me a comment down below in what things you believe I can improve for the next videos. Thank you very much. Bye.